So therefore,
oh, but I was saying like it's C is just a shorter version.
All right, who would like more time to look through these 4 problems and talk about which one does not belong in their opinion? All right, who would like to share out loud which one they chose and why? Who would like to share which one they chose does not belong and why? Ellie?
I chose A because there's no multiplication whatsoever, whereas all the other ones have at least one component of multiplication.
This one has no multiplication whatsoever. All right. All right, who said something different or chose something different? Jesse?
I chose B because it's the only one with addition and multiplication.
As both adding and multiplying. All right. Did anyone say something different or choose a different option? Bless you. Bless you. Everyone chose those first 2? Okay, what did you guys notice as you were kind of looking at and describing these different sequences? Well, sorry, not sequences, these different expressions.
A and B are equal.
Okay. That is true. Options A and B are the same value, and C and D are the same value. How did you figure that out, Jesse? Did you just like solve it, or?
Well, I mean, I was too lazy to solve it for a long time, but I just assumed that there were 6 2's, and so 6 times 2. That's 5.
So there are 6 2's that are being added, which gives me 12. Right? But also 6 times 2 is 12.
And you have 5 of that, and they're both 17.
Yeah. 2 times itself 6 times is 216, you said?
I have no idea.
No idea? But that is the same as 2 to the power of 6, right? What do exponents represent?
That times that, a number of times.
Yeah. How many times do I multiply it by itself? Right? So this is really the same thing multiplied 3 times. So 2 to the power of 6 means 2 being multiplied 6 times. So that means that these are the same. And 6 times 2 actually means adding 2 6 times, which is why it shows it like that. Okay, so these are equivalent and these are equivalent. Questions on your warm-up. Now, are we familiar with this activity on which one doesn't belong? You guys know that you could find an option, a reason for any of these, right? Okay, move on. So we're going to talk about activity 2, more paper slicing. We're at the bottom of page 47. So we're going to examine a table from the previous lesson. You're going to work with a partner or group on this activity, and then we'll do some discussions. So take a look at this table. Does this look familiar to anyone? Yes. This table is from lesson 2, I believe. Okay, where I gave you guys this piece of paper, where we cut it in half, stacked it, cut it in half again, stacked it, cut it in half again, stacked it. What was the pattern happening for the area? It halves, which means it's multiplying by 0.5. Now, again, this isn't in your books, but if I asked you guys to write a recursive equation for this, how would I write that?
F of n is equal to F of minus 1 times 2.
Divided by 2? Okay. What is the other part of the recursive here, though? That first part. Is it f of 1?
No,
So it's F of 0.
Ooh, yeah. So usually we say f of 1 equals that first number, right? Why do I say f of 0 this time?
Because it starts with 0, because like nothing they have it.
Yeah, so I talked about a couple lessons ago that sometimes these have like term zeros. Not everything has a term 0, but this one does, because if we're counting the number of cuts, when I start off with that fresh paper, there has been 0 cuts. Okay, so this is the recursive for that. And if this is f of 0, then this would start at the next term, which would be 1. Okay? Questions on the recursive pattern for the paper problem we saw in lesson 2. Okay, if you would like to write that down, you can, but you are not required to. It's not part of the questions. Okay? I just wanted to kind of like bring that recursive back into this previous idea. Does anyone still need what's currently on the page? I see some people writing. I'll wait. Now, as I talked about earlier, this pattern helps me describe the sequence. It doesn't help me predict terms that are way in the future. So if I said, okay, well, what is the area after 20 cuts? That equation wouldn't help you. However, we have a student that found an equation that she can use to figure out that value, which we're going to look at next. We good? Okay. So a student, Claire, same idea. She takes that piece of paper, it's 8 by 10, she cuts it in half, and then she does it over and over and over again. But instead of doing the recursive definition, she writes this equation. C of n equals 80 times 1/2 to the power of n. I'm going to go ahead and circle that or box that because it's important. C is the area in square inches, and n is the number of cuts. So this is the area after n cuts is equal to this equation. Go ahead and talk with your group. Explain where the different parts of her equation are coming from. Okay, where is she getting each of these parts? Go ahead and turn and talk.
I was just like, first
All right. Who needs more time? So where is the different parts of this equation coming from? We have 80 times 1/2 to the power of n. What is this coming from? Jesse?
The 80 is 0 or the first term in the sequence.
This is what we started with. Okay. Where are the other parts of this coming from? Someone else. Where are the other parts of this coming from? Math. The rule. Okay. Not just like the half, but the fact that we're multiplying by a half, right? And then why this exponent of n?
because it's telling you how many times the thing comes by the half by itself. If it was 100, then you would get a fraction to multiply the starting value for to get the end value.
Okay. This is how many times you multiplied by that 1/2. Because if we think about what was happening here, right? If I cut 4 times, then I cut that 80 in half 4 times. I did 80, cut in half, cut in half, cut in half, cut in half. Well, how many 1/2s are being multiplied? 4. So I can also write this as just 80 times 1/2 to the power of 4, since exponents since exponents and repeated multiplication are the same exact thing. Okay, so taking a look at our equation now, do we have any questions about where the parts of this equation came from? Why we have the 80, why we're multiplying by 1/2, and why we have an exponent of n? Okay, here's what I want you guys to do. Using whatever method you feel is appropriate, see if you can find what the area is after 10 cuts. Okay, after 10 cuts, what is the area? You can use Claire's method, or you can use a repeated pattern by building your sequence, making your graph, making your table, whatever. Okay, but go ahead, let's take about a minute or so. What is the area of the paper after 10 cuts?
I got 11,000. I don't think I did that right. Okay, so 1/2 times 10 is just 5, right? Times 10 is just 5.
No. 1/2 times 1/2.
Oh.
So because it's 1 on top, the 1 stays 1.
Is
And
what
then
the
the
parts
two-
that we use.
So I'm getting 1.
So the 80
Let's do this one.
is how much area you started on. The pattern is actually This is what I like. And because I'm repeating multiplying half, raise it to an exponent of 10, because that was on the. So now that we know that dividing into half is so many, figuring out what is the area.
So it's never gonna get negative, so just kind of.
So we can do that. Yeah. So technically, if you multiply half over and over and figure it out, so you never eventually get, you may never get to your destination. So one. So you would times 80 by 1/4. No, I did 1/2, 10 power. Yeah, that's what I did. And I got like 11,000. Oh, we got the 7 I don't, let me try this again. I probably did something wrong, so. I got 800. Where did this come from? This, what do you call it? One, yeah. 1 divided by 2, then it's that, and parentheses. And then it's exponent 10. So you see what I did here? Because technically, if you're doing that, then you're doing the exponent. But that's, wait, okay, hold on.
Yeah. Give me 1 second, guys.
That's how I got mine. Is this? Does that number look reasonable to you? I don't know. As I'm cutting in half, it's even smaller and smaller, right? Cutting in half 10 times. Long cuts. So what?
Hold on, I'm gonna freeze this for a second, because as soon as I press this button, it's going to erase everything.
Yeah, Ellie probably makes sense.
You know what? I just won't freeze this.
The area of the 800,000 after the area.
So, If you think about the area, after 4 cuts, it's already down to 5.
Yeah.
Right? So after 5 cuts, it's at 2.5, 1.25, like
0.51.
not 0.75, but like point.
0.15.
It's like 0.625.
Yeah.
So after 7 cuts, it's at 0.625. We're already less than 1. We're getting pretty small. That's going to keep cutting in half. 0.3 something. 0.1 something. So does it seem reasonable?
Yeah. I think the reason I was wrong because I thought it meant by 0.5 instead of 1/2. Because
You can do that.
okay, so I did do that and that's how I got it.
Hold on, not 1.2, 1 divided by 2.
Well, yeah, but also what I thought, it was like, if you put, there was a D in that equation. I don't know where that D came from. Like, it was not supposed to be there.
It's supposed to be something.
Who needs more time to find the area?
Yeah, that was something.
All right,
So if you wanted to do that, I'm pretty sure.
finish up your conversations and let's go ahead and talk about our answer.
Like 40 first times, because once you click times, then it's assuming that there's an unknown number there that you're supposed to multiply by. Maybe, yes, but you were doing it, you were hitting times instead of going directly to the exponent. You're not
Okay.
multiplying.
Here's the number that you should have gotten for your area after 10 cuts. Everyone look at the board, please. Okay, very small number. You might be thinking like that's way too small, but it's pretty reasonable, right? Because that area is going to get smaller and smaller, and because we're multiplying, it's exponential, which means it's going to be getting real small. Okay, who did this by plugging it into the equation? Half of us. So let's before I get to the equation, who did it by just dividing by 2 repeatedly? Okay, is that going to give me the 10th number? Yeah. If I start off by 80 and just take my calculator and just divide by 2, over and over 10 times, that will get me an answer. Okay, the other option there, using Claire's equation, is like I can just plug in 10 because n is the number of cuts. Now to do that, I just have to use my calculator. I can literally just in my calculator type in 80 times 0.5 to the power of 10 equals, I get my answer. Okay, now both of those methods are perfect. There's nothing wrong with them, but which one of those is going to be quicker to do? The calculator. Okay, what if I then asked you like a part C, find the 30th term? Find the area after 30 cuts. Are you going to want to sit there and multiply 20 more times? Or can we just plug in 30? 80 times 0.5 power 30. Lots of zeros, 75. Okay. Does anyone want to see how to plug that in on the calculator so we're all clear on how to plug that in? Yes. Okay. So I'm just going to pull up like a basic calculator. So if I use Desmos, the scientific calculator that is like on your guys' homework, that one's pretty easy to type in because you can make it look exactly the way you want it to. So I can do 80 times 1/2, and then I got to make sure that I click over, and then to the power of 10, and I automatically get my answer. I don't have to use extra parentheses on this one. I can if I want. So if I wanted to do times 1/2 and then to the power of 10, I still get my answer. You can put 0.5 in here instead of 10 if you want. If I don't have a calculator like this, I can pull up a calculator on my computer. 80 times 1/2 to the power of 10 equals, so that's 1/2 to the power of 10 times 80. So my calculator gave me a little bit of troubles. Okay, so you may have to do the exponent first, power 10, and then multiply it by your starting number. But still pretty quick when we compare it to multiplying 80 by 1/2 10 times. Okay, questions on Claire's equation? All right. Why did it? Hold on, now it's wigging out. All right, so go ahead and turn to the next page where we're going to take a look at Kieran's work. Now, Kieran is going to be messing with the paper in a different way. He's not cutting it in half. What he's doing is he's taking the same piece of paper, length 8, width 10, and he's cutting away an inch, like a column, every time. So he's cutting away a column, which means he's taking away 8 squares, and then he'll cut away another 8 squares, cut away another 8 squares, over and over. Okay? Here's what I want you guys to do. Fill out the table for this situation. Do you guys want to see that work happening to help you, or you got it? So when you complete your table, all right, so if filling out that table, it should be pretty quick. We should see that the area after one cut is 72, because I took away that 8 inches just once. Then it's 64, which is already in there. Then we have 56, 48, 48, and 40. Are there any questions about how that area is changing with every cut? So we know the rule that's happening here. We understand what's going on. All right. So Kieran says that for this area, after 6 cuts, the area is 80 minus 8 times 6. Again, turn to your group. Where are the parts of this expression coming from? Where are the parts of this expression coming from? And then see if you can write a definition for K of n that is not recursive. So see if you can build a repetitive equation using the pattern from the table, the pattern from this expression that is not recursive. Start off by where do parts of that expression come from, and then see if you can manipulate them.
So if you were to do 80 times 2, which is 21,621. Wait, what is yours with it? What is my looks at this? That's 24, not 21.
That's fine. Oh, wait, no, minus.
Mine's the
that.
first. Times what?
Times it, it's not an exponent.
No.
Because it's an exponent of the 8 by 8 is 7. It's just kind of
Oh. Yeah, no, it has to be good. To the third power is 112.
Inverse.
If you were to
What?
do it
And the term with the reverse equation
you're
is?
gonna do it exponent.
No,
If
so
you want
but a recursive.
Like,
Oh,
the
it's
base
What's the
to the
definition?
third power,
So it's
it's
not
like the equation.
that has like
But it was just in some
as
sense.
one equals one, and then it's
Or you just put it right on the.
So recursive is
I'm
an
just
equation.
saying.
So see if you can make an equation that's not repetitive, kind of like how Claire's was. So I can just plug the number and I get an answer. Right? With recursive, if I plug the number, it's not going to be the answer.
Oh,
So see if you can come up with an equation that you can just plug in one value and give you the answer.
okay.
What about this?
Because after this, we're gonna actually define what that equation is called. So,
I'm just like, I put my.
all right. So breaking down the expression, excuse me, the expression first. Where is the 80 coming from?
The starting pattern.
Again, 80 is that start value. It's how much area we started with before we did anything. Where's the minus 8 coming from?
How much we're taking away from each.
Yeah, that's our rule. That's how much we took away on each cut. That was what was happening every time. It's how I predicted the next value. And then what is the 6 representing?
How many times we're taking away.
Yep, number of times we subtracted. So we have some similarities with Claire's, right? Both of them had a starting value, both of them used a rule, and then both of them repeated that rule. In this case, did they use exponents to repeat? No, they used multiplication to repeat. Okay, so using that idea, if I wanted to build an equation for n cuts, it would be k of n equals what? 80 minus 8 times n. That is correct. 80 minus 8 times n.
So do you put exponents for multiplication and then like put the letter right next to it and you're like doing like arithmetic?
So, yes. So Ellie asked a good question. So if we're doing multiplication every time, it's like an exponent. And if I'm doing adding every time, I just put the number there. This is something that we don't really think about. When you think about like what is multiplication, we don't really think about what multiplication is. Multiplication is repeated addition. If I add over and over and over and over again, that's multiplication. That's where it comes from. If I multiply over and over and over and over again, that's an exponent. So our arithmetic sequences repeated over and over and over, they show up as multiplication of the number of times I added by what I was actually doing. Okay? This is familiar because it looks kind of like this. Does that look familiar to anyone? Linear, right? If I just put this in front, negative 8n plus 80, that'd be your normal linear equation. Okay? Linear equations is a pattern of constantly adding the same number every time, just like arithmetic. When we have geometric, It's that pattern of repeatedly multiplying over and over again. When we repeatedly multiply, that shows up as an exponent, which if you've ever seen an equation that looks like this, that's an exponential equation. Okay, so this is something we don't really think about, that when I repeatedly add, that's the same thing as just adding that number times how many times I added it. When I repeatedly multiply, that's the same thing as multiplying by the number to the power of how many times I did it. So here's what I want you guys to do. We have K of n right here that we just built, and then C of n from the previous page. What value, use the equations, what value is bigger, C of n or K, sorry, C of 6 or K of 6. Use the equations this time, don't use repetitiveness. Plug 6 into your equations to find the two values. Do you guys want me to write C of n back up here? Okay. C of n from the previous page. Is right there. And K of n is right here circled. Go ahead and find C of 6 and K of 6. Which one's bigger?
Oh, which is larger? I can read. Yeah. This is just this many times. Maybe that's why.
I don't know who's in grade.
Yeah.
It's cool.
Yeah, he's an elementary. He's young.
Yeah.
Well, yeah, we were supposed to, but we did. Yeah,
We did.
I don't know, because
Yeah,
one of us
sorry.
asked about it, it might have been.
Yes, page 16. Wait, no, that's a wrong spell.
All right, who needs more time?
It was a.
All right, so can someone tell me what was the value of C of 6?
C of 6,
Yes,
1.25.
that's correct. So the area after 6 cuts on Claire's equation was 1.25. What was the area of Kieran's equation after 6 cuts?
36.
32 is what I have. Yeah, because it would have been 8 times 6 is 48. So 80 minus 48 is 32. So the bigger value was Kieran's equation. And I could find this information by just simply plugging 6 into either problem. Does this make sense logistically?
Yeah.
Yeah, which one's gonna decrease more quickly? Cutting in half, something exponential, or subtracting something arithmetic? Yeah, it's going to be exponential does things much quicker than arithmetic does. There will be a point when like that is reversed, where arithmetic would be the smaller of the two values, but most of the time arithmetic just doesn't grow as fast or decrease as fast. Questions? So these two equations we're just looking at are examples of defining the sequence by the nth term. So these are called nth term equations. We call them nth term equations because they help us find any term. You'll also see these defined as maybe an explicit equation or a direct equation because they help me find the value explicitly versus using a reoccurring pattern. Okay? Like I said, these equations are more closely related to the linear and exponential equations you may be more familiar with seeing. Okay. We're not going to do that one. Let's move on to our last activity. Activity 3, a Sierpinski triangle. Sierpinski, the triangle one. We're going to continue to practice finding terms of a sequence, and we're going to focus in on an important piece about these explicit equations. So here's that triangle pattern we have seen a couple times so far. Again, the pattern is that we start with one equilateral triangle, and then on the next step, we break it into 4 equilateral triangles, removing the middle, and then every shaded triangle, that same pattern happens. Let S be the number of black triangles in every step. Go ahead and with your tables, define S of n recursively. So this is not nth term, okay? So using your 2 equation, the one that looks like this, go ahead and define the equation recursively where we're counting the number of black triangles. That's the pattern we're looking for, okay? So go ahead and figure out the pattern and build a recursive definition.
Is it times 3? Yeah. So it's I would ask you 0 is equal to 1.
Dividing it into 4 triangles.
Well, isn't it, every each time you get 3 new triangles,
You get 3 new triangles, but you're dividing the triangle into 4. And then subtracting 1.
so it's S of 0.
This is correct.
That's double times 3, like S of 1 is 1, or times 1, S of n is S of n minus 1. It's like it's something. That's the one I did a couple lessons ago.
I don't know what I have yet.
Oh, wait, yes.
I don't think you're good.
If you can't divide.
All right. So what is the pattern? So if we count the number of black triangles, we have 1 here. How many do we have after that? 3, and then 9, and then we have 27. So what's the rule happening here? What's the pattern? Timesing by 3. Okay, so it's important to first figure out, like, what am I even doing? So now with recursive, how did you guys write the starting value? S of 1 equals 1? Did everyone write it that way? Okay? And then to write the pattern, S of n equals S of n minus 1 with what done to it?
Technically, wouldn't it be S of 0? Or wouldn't it be 0? Because technically, aren't you starting with one black triangle?
Let's have the conversation here in just a second. Let's finish off this equation. So if I start off with term 1 equals 1, and my new term will be the previous number times 3, then this would start at n is greater than or equal to 2. Does the pattern explicitly say that is term 1?
No.
Could I be like, I think it's term 0? If we did that, would that change parts of the equation? Yeah, not the entire thing, but it would change parts. I'll write this in red. If I said, oh, that's my term 0, then S of 0 would be 1. S of n would still be S of n minus 1 times 3. But then my n value would start at what? 1. So this is an alternative equation. Both of these are correct depending on how you determine what term we're starting with. Okay. Questions on what is happening recursively for this problem? Starting at 1, we're multiplying by 3, and we wrote it that way. All right. So here are some student work here, Andre and Lynn. They were asked to write an equation that was not recursive. They have different equations. Here's Andre's equation. And here's Lynn's equation. Go ahead and have a discussion with your groups. Which equation do you think is correct? Explain or show your reasoning. Okay, go ahead and try to talk. Out of Andre and Lynn's work, which one do you think is correct and why?
How can something be before 0?
But how can you have n as greater than 0? I mean, I guess we could. But we didn't have to.
So that would work. This one would also work. Well, if you were going to do the term shown right now, so you're going to take just one, then you do something like 3, right? That's 1. But 3 compared to the opposite factor minus 1 is 2. I think it's 2 now.
But does that, but does it mean that you subtract the 2 or you subtract the number you got after this video? So like say I say 3 times, say 3 times 3, it's 9, right? But when I minus 1 and get 8, or when I minus 2 and get 6. Okay, yeah. Because if you keep subtracting 1, you're getting that number off, and that's how you get that number. You just subtract 1.
No, it doesn't work. Obviously, because if you were going to go, since n is like the actual number,
Okay,
the
so-
actual step that you're on, if you were on step 2, then 3 times 2 is 9, and then is it 9 blacks? Where do you
And okay, so then both of them.
No,
Because
this one's right.
how is that right? Because so if you take no, so okay, so the reason Audrey's work, well, okay, so Audrey's would work, but the thing that's tripping me up is the end is greater than this.
And
Yeah.
Andres is like, and how? Okay, so, right, 3 times 3, so
Is
3 to the
9.
x squared of 2 is 9. But on the second triangle,
So 9
it would be on the second triangle, and there's 3.
there's 3.
This, would that be 0?
That would be, oh, so how would you get 1 then? So you would put in 1 for the first triangle and get 3. For the second triangle, you would put in 2 and then 6. Yeah, okay, so, no, so I'll just have it. Because if you plug in 1, you get, you plug in, oh, these 3. If you, how do you get it?
This one, he's saying that this starts with 0. This is 0. It starts with 0.
Okay, so,
And
zero
times
is
0
zero.
is 3 to the power of 0 is 1.
Because then,
I keep forgetting that that's a thing.
That is a thing.
I never learned that. Okay, hold on.
3 to the
So
power
then
of
yours
0.
just,
But also Lynn is correct because
I'm just kidding.
since she says that this one is 1 and this one is
Finish up your conversations in the next minute.
They're both right. They're both right. They're both right. They're both right. So what is the difference?
okay, so if you plug in the number that you would for Andres, you would get a different number. If they were both right, you would like, say they were both right, you would get theoretically the same number. You would get a different number for every time you put in Linda and Andres. If you get 2 different numbers, that means they can be both right. They
No,
both
they're both right. No, they're both right. See, I think Audrey's, like, see, his starts with 0 versus 1.
Yes.
He says his starts with 0, which is totally fine. But Lynn says that hers starts with 1. Yeah.
Okay, so 1, and this would be 2.
The first one, Andres, he's saying this is 2.
Okay, so for,
Lynn is saying, no, this is term.
so for Lynn,
But that's not what
it's
they're
both
saying.
0, 0, and this is 4, and this is 5.
We talked about that. It doesn't explicitly say, so is that part wrong? You can think about it this way. So now,
It says it's
Andre
That means
thinks
that
that's term 1.
there was one before this one, and this one is the second term.
To get the third term, I will
I'm waiting until she says something. I don't even.
Fourth term. No, I get what you're saying, but like. So are they both saying that they're? Right, or that's 0. So.
No, wait, this is term. Number starts at 0. This one starts at 1.
That's not what it says. It says that it's the equation starts at what? On term 1, I see it right off. You can go from the, what do you have?
So this one
So are you
is
saying that?
0.
I feel like they're both 0. No, this is step 0.
But if they're both 0, then if you plug in the number, you would get a different answer to both of them. So say you put in 3. So would you put in 3? That's what I was saying. If you put in, say that they're starting at the same number. Say that they're starting at the same number.
Step I'm on. That's what the discussion's going to be about.
What did you guys say?
All right.
You said it.
Let's go ahead and discuss Andre and Lynn's work. Who's right and who's wrong? Andre's correct. What about Lynn? Is he incorrect?
Okay, so here's my thinking.
Okay.
Like, it doesn't say that n is the starting number. So, well, 1 is the starting number, so therefore 0 could be the starting number, but also 1 could be the starting number.
Okay. So let's talk about that. Because that is exactly right. We just talked about with question 1 that they didn't really specify it could be term 0, it could be term 1. They don't tell us that explicitly, do they? No. So what Andre is saying is like, oh, well, this is term 0. Right? That's what he's saying. Lynn is saying, no, this is term 1. Okay? Neither of them are incorrect. But then if we look at those actual equations, okay, starting at term 0 for n, and starting at term 1 when it has n minus 1. Let's think about what's actually happening, okay? If this is term, would it be better if I made a table? Would that help for visual purposes? Yeah? Okay. So let's look at Andre's first. So Andre is saying we're going to start at term 0. This is term 0, 1, 2, 3. There's 1 triangle, 3, 9, 27. To get to term 1, how many times did I have to multiply by 3? Once. To get to term 3, how many times did I have to multiply by 3? 1, 2, 3. To get to term 5, how many times did I have to multiply? 5. So he's noticing that, like, oh, I'm just going to take 1 and I'm going to multiply by 3 the exact number of times as what step I'm on. Now, multiplying by 1, does that do anything? No, so he just simplified this as 3 to the power of n. Because I'm multiplying by 3 the number of times as the step I'm on. So that was Andre. Now, Lynn, he says we're starting at step 1. So this is the first 4 steps. 1, 3, 9, 27. So he said, okay, I'm starting at 1. I'm multiplying by 3. To get to the second step, how many times did I have to multiply? Once. To get to the fourth step, how many times did I have to multiply? I didn't multiply 4 times. Because I started here and I did 1, 2, 3 times to get the fourth term. So if I did like the 10th term, how many times did I have to multiply? 9. 1 less than the term I'm on. So we changed his exponent to be 1 less. Because I'm multiplying 1 less time than if I had started at term 0. And again, multiplying by 1 does nothing. So you just add 3 to the power of n minus 1. Do both of these equations give me the correct numbers for the sequence?
No.
Yeah. The difference is Andre was looking at this as n starts at 0. And, geez, I can't even cut. N is more than 1. Neither of them is right. Neither of them is wrong. It's all based off of how they viewed it. So this is an important piece to this non-recursive idea. In the example of the paper cutting, on both of those equations, that 80 was term 0, right? So to do the first cut, I only have to do that operation once, which is why our exponent was n. If I start on a different term, other than the 0 term, then that means I'm multiplying less times than if I started on term 0. Questions on, so the answer is both of them are correct. Okay, both of them are correct. They're just they're assuming that we're starting at term 1 versus term 0. Questions? Okay. We're going to skip the try this, so if you want to go ahead and turn to page 50, please. Okay. Here's what I want you guys to do. And you have a little bit of space at the bottom of page 50. This is our synthesis. I do want you to attempt this. I know we're kind of running out of time. I will give us more time beginning the class tomorrow if we need it. I want you to pick one of the 2 sequences up here. I don't care which. Pick C or pick E. Write an nth term equation for it. We will share our equations and we will clearly talk about the differences if you started with n equals 0 or if you started with n equals 1. Am I telling you which one to start with? So that means you get to choose. Okay, so pick one of the 2 equations and write an nth term equation. I have the examples up here written on the whiteboard if you need to take a look at those examples and where the pieces come from. Go ahead and on the bottom of page 50 where you have some open space, pick one of the sequences and write an nth term equation for it.
could see.
Seven times zero would be zero, and then 1 minus zero is nothing. So why would we do 7 times 1 would be nothing?
You impressed with my skill? All right, who needs more time to write their equation? All right, here are the possible answers I would accept. All of these are correct. I think the only one I really need to like adjust is maybe on these ones, you could have just had 2 power n or 2 power n minus 1. Because multiplying by 1 changes nothing. Okay. What questions do we have about why these are the correct non-recursive equations? Ryan?
How did you get, for the first scenario, how did you get n is greater than or equal to 0?
So that was a personal choice. If I say this is my first term, then that means n starts at 1. Starting at 1, multiply by 2 repeatedly. But because I started at term 1, that automatically means that I have to subtract 1. Okay, so these are linked. If I start at term 1, that exponent has to be n minus 1. Same here for the arithmetic version. Because I start at term 1, the thing in the parentheses has to be n minus 1. Now, if I look at this and I go, this is my term 0, I'm making that choice and I think that is term 0, then n starts at 0, and I don't need to subtract. Because to get the first term, I would have done my operation once and it matches. Okay, so that's n, if I start at 0, then I get to just use n. If I start at 1, then I have to use n minus 1.
Okay.
This might be something helpful. That's one big piece of today. The other big piece is using exponents if it was geometric and using multiplication if it was arithmetic. Are there any questions about that? Okay, all of the examples on my big poster back there, on every single example up there, I have it as starting at term 1. Okay, on every single example back there, just to keep it in line with the recursive equation that also started at step 1. So you don't ever have to, like here, you had a choice, right? The only time you don't have a choice is if it explicitly tells you this is step 0 or this is step 1. Okay, so we're going to go ahead and start our homework. unless there's any more questions. Okay. Your goal today was to understand that different equations can represent the same sequence and practice building those. On your homework for today, the first two questions is going to be having you guys really think about that non-recursive definition, this nth term. Everything after question 2 is going to be reviewed from previous lessons. Okay. I just want to give you guys that heads up on question 2 though. Section 8.
You cannot access this.
Oh, did it not open it because it was being dumb earlier today or yesterday? So if it's not letting you access it, it could be because with the whole learn zillion issue yesterday, it locked you out. So I'll come over and help you. But on question 2, guys, I want to point this out. Try that again. There we go. On question 2, I have you guys write an equation. It does explicitly tell you your starting term is term 0, which means that there is only one correct answer here. You don't have to choose which one to use, unlike your cool down. Does that make sense? Okay. I'll let you guys work. We get out of here in about 15 minutes. So I will be giving you guys another 15, 20 minutes tomorrow. Okay? All right.